Welcome you to the next session of embedded software testing, lecture 8. Here we go through software lifecycle. Positive, some issues. Oh, it is going already. I think it's recorded something. That's why I'll restart it. To embedded software testing, the lecture session 8 of embedded software testing. In this session, we will study some of the life cycles that are followed for embedded software development and testing. Typically, it is both, and in detail, we will understand what are specific software testing lifecycle process elements that are required. So, we need to know some of the definitions of entering exit criteria. Then there are sample prototypes of life cycle. Basically, we need to understand what is life cycle, what are the elements that are required to have an life cycle implemented, how it is organized. Examples we'll go through. Then we will study in detail about software testing life cycle per se. And before that, I'll just re-emphasize what we studied in session 7. We started with an exercise for lecture 6. Then we studied about TM method. This is one of the important method that is being followed. What it does is it will understand all the characteristics of the complex system or the embedded system of the test, and it will apply the approach from various generic methods. So the principles are V2, life cycle, infrastructure, techniques, organization. So we studied about each one of this life cycle, techniques, infrastructure, organization. Then some of the characteristics that needs to be laid down for each of the embedded systems in terms of safety critical or hardware restrictions. Basically, the behavior of the embedded system under test needs to be characterized. So based on that, we will apply the TM method. Then we had gone through some of the commercial tools. What are those categorized in terms of measurement or in terms of editing, in terms of debugging. So all these are categorized. So these are some of the basic categories of commercial tools. So we had an example of snapshot of typical embedded system tools. Also, we studied about the words, different words. Okay. What is software lifecycle? We know there are various stages of software development and testing at different levels are used. So those need to be considered for implementing an embedded software system and testing. So those stages of development are to be used or considered at different levels. That is nothing but software lifecycle stages. So some of the points are processes to be there. There should be a defined process for stages of development and testing, and the lifecycle should consider all aspects of software development such as requirements, design, implementation, and again requirements could have derived requirements, requirement studies, requirement analysis. Then design will have a high level design, low level design. Implementation can have a low level implementation and debugging, testing. So all this should be considered in terms of the complete software life cycle. In essence, the complete software life cycle will be divide into multiple software life cycle. So in general, what they do is they do a one stage prototyping life cycle, then they will go for a formal life cycle. These two typically they are using it in terms of embedded software system. Of course, there are different types of life cycles that is going to be applied for each of them, or the way how they want to organize it. Basically, in industry to implement some embedded software system, they first do the prototyping, then they do the formal development. So the prototyping will have a prototyping life cycle, the formal one will have a formal life cycle. So we will go through each of these, how it is defined, what are the differences, etc. Before that, before we study the prototyping and the formal life cycle, we will have an understanding of a couple of words which are important: entry and exit criteria. So we know that a software life cycle will have different stages or elements of the life cycle. So each life cycle or the stages have to have an entry, have to have an exit. That means, what is entry? Entry is nothing but the conditions that must exist before an activity or unit of the defined project life cycle can commence. That means before we start of the life cycle, the conditions that are required to start that activity has to be existing or should be available. So that is the criteria to start that. That is why it is called entry criteria. Exit criteria: the conditions that must exist before an activity or unit of the defined project life cycle can be deemed complete. That means it's the other way. Before we announce or before we tell that that cycle or that activity is complete, there are different conditions or criteria. Those need to be satisfied. So those are all called exit criteria. So these two are very important items that they use in defining the software life cycle for each of the stage. Stage 1 will have a entry criteria conditions. Stage 1 will also have a exit criteria of different conditions. Similarly, stage 2 will have an entry criteria for that stage and exit criteria for that stage. Similarly, all the stages of the life cycle will have entry, exit, entry, exit. These two must exist for moving into different stages of the life cycle. It could be any life cycle that you take. This process is very important. So some of the considerations for entry and exit criteria are as below. It is dependent and must have essential. That means entry and exit should be in place, and it's a dependency on that particular stage. So without this, it will not move. Then what are the expected deliveries or expected deliverables in that stage before we call it as a exit? There are certain deliverables that stage ends with, so that is part of the exit criteria. Then how it transits: entry, re-entry. That means suppose the stage 3 can be said as complete by defining uh, so and so deliverables, and so and so deliverables have to be placed before moving the stage 3 into stage 4. So that stage 3 to stage 4 transition will have a defined elements. Those elements are called transition criteria. Transition from stage 3 to stage 4. That means the stage 3 will have some entry, the stage 3 will have some exit. Also, the stage 3 can re-enter again based on certain conditions getting transitioned within that. So that is also called entry, re-entry for that particular stage. And entry exit criteria condition considerations should identify participants or stakeholders for that. Identify participants or stakeholders. re-enter into the same stage or process, nothing but re-entry transitioning. Expected deliverables are for each of the stage, and there are certain dependent and must have items for each of the stage that needs to be identified. So basically, that must be considered. So that is these are some of the considerations that needs to be used for entry and exit criteria of the life cycle process elements. Okay, so we know that prototyping life cycle and formal life cycles are used in general embedded software development and testing. So what are those? We'll uh, go through. Prototyping life cycle. So typically, prototyping life cycle is something like this. You can see a lot of blocks that are involved. So as I said, there is an entry into the life cycle of the prototype, and there is a exit. I will explain each of them. There are this dotted block is nothing but the life cycle of the prototype. So it starts with something like there is a box which is nothing but an entry. We will go through what is that box means. Similarly, to come out of this life cycle, there is another exit mechanism. The bottom you can see. Example is system specification is an entry. Formal software life cycle is an exit. That means it is ready to go for the formal life cycle. It is the next stage. As I said, example prototype life cycle. What I discussed is these are prototype life cycle entry and exit items which are mentioned for this life cycle. So prototyping life cycle. The software development is initiated using an iterative development model in order to freeze the high-level requirements definition to validate the software architecture and software performances. That means primarily what we will do is something like we will identify a iterative model, and the goal is to identify and freeze the high-level requirements, and we should be able to validate in a way the architecture what we have defined by the prototype, and the software performances what it would be to perform the various requirements that are required. And during prototype development, iterative description of software requirements, software architecture, design, source code, and test cases will occur to lead to a software requirements release. That means majorly we concentrate on releasing the requirement, releasing the architecture. Majorly it is a software requirements release, but to release that requirement, we need to have some sort of a prototype architecture, prototype design, prototype source code. Something like prototyping the various aspects to prove that these requirements are viable. And to do this, as I said, these elements are the items that are covered under here should be configured. So what we do is we will have a configuration management also, configuration management process, and all the items produced during this development will be configuration managed. Means it could be a architecture, it could be a design or source code, all this part of the prototype. All those should be configured, and they should be under configuration management. So this life cycle will have all these elements covered under the prototyping, and no formal change request management will be performed during prototype life cycle. So what is performed is these three bullets. What is not there is there here actually. That means there is no formal change here. Formal means from the end system perspective, from the user's perspective, or from the customer perspective. So customer has given an end requirement. To achieve an end requirement, what we do is we will divide the end requirement or the formal stages of development into prototyping, and the prototyping we will not release to customer. It is something like an internal definition or proof of concept. Also, it is called proof of concept. is one of the very important thing that embedded system industry they are following. So proof of concept is something like an internal development or testing process. Of course, it depends on the management how they want to project this. Customers also can be involved, but basically it is for an internal confidence, internal as well as within a defined framework. This framework is nothing but the prototyping, and once we are good to go for the formal life cycle, uh, there could be some sort of approval from customer, so which will take as an important step or stage of the prototyping, so which is nothing but the exit criteria. And for doing that, we may need or we may not need a formal change request management, which will be used for prototyping. That means any of the findings, defects, and whatever we do for doing all this software architecture, design, source code, and all may not require a formal framework. It will all be internal defined. So no formal change request management will be performed during prototyping life cycle. Problems are recorded and reported to the system specification process using an action item follow-up list. That means a simple action item list will be there. I will explain one of the slides how an action item list will be used. It is also called MOM with action list. So this is a follow-up list or an action item list that will be used. As I said, during the development of the prototype, there could be some bugs or some revisit into the architecture or some feasibility updates. This needs to be reported. Uh, these are all part of the system specification, because we are not still done with the requirements. So that is very important that the specification is thorough and solid in the prototyping. So that is one of the important criteria before we move into the next stage. Uh, for doing that, we will have a team discussions that are organized between system team and the software team. And one thing that we need to know is that the system is usually defined with the help of customer as well as with the help of the system people. It could be management or the seniors. I would not say seniors. Customers also can be involved, or a customer representative. So this is at the system level, and the team which are responsible for implementing team implementation, testing, development, whatever it is, QA and all that you can call. So that is nothing but the embedded team or the software team. So these two will closely work and interact to make it the specification process to arrive at completion of prototyping or the prototyping lifecycle. So it's an iterative model. As I said, the prototyping is an iterative development model, sort of iterative. I mean the process items which are there within the prototyping, like architecture, design, source code, and test cases, will be iteratively developed. As we progress, we will revisit again and again to conclude on those items. So that is an iterative model during prototype development. Iterative description of software requirement, architecture, design, code, test will occur. So finally, the end goal is to use the exactly needed software requirements that will be released, and all these items will be configured, because Sometimes what will happen is before we do the or while doing the formal updates, we may need to revisit what is the basis on which these decisions are taken care, some of the decisions are taken care, etc. It is also called as a POC, proof of concept. It is basically an internal development or confidence gaining stage. Yeah, customers also can involve, and there is no formal inputs or changes are recorded or taken considered for the prototyping, and the system specification process will be arrived with the help of the stakeholders, initial stakeholders like system team or software team. So these are some of the prototype lifecycle items. I will explain with an example software prototyping lifecycle. You can see there is a dotted block. This block is prototyping software lifecycle. This needs to be entered, then it is called software lifecycle kickstarted. For that, what is the input? System specification. System specification could be a customer given draft. Customer given draft specification. System team or customer. So this is a starting point. So that's what I mentioned. Entry into life cycle. We'll start with this specification because what we are going to prototype we need to know, right? So there has to be some draft of specification. So with the help of that, the life cycle kickstarts. So what are those that are required? So what we do in the first stage, prototype initialization. So we'll start with the stakeholders, team identification, who will do what and all that. And those initialization, as a result of that, we will come up with a SRS or a DD. Here SRS means software requirement specification. DD is detailed design, or sort of called is called architecture. You can also define as an architecture. I have put an example. It could be this, it could be the other one also. But the flow is whatever the arrows or the entry. These are all some of the primitive items that needs to be there for prototyping. Then once we have this stage with the initial SRS and the initial design, we will do an iteration of these items by defining, realizing and evaluating. So this will keep on getting done, and as a result of that, it could result a system specification update, and the same system specification is to have a updated SRS and design, and that design and SRS will go through definition of that realization. Here realization means what we do is we will try to implement our feasibility and try to understand. So basically what they do is we do some sort of modeling. That is in the offhand system, what they do is they develop different models connected, how they interact, what are the interfaces, what are the signals likely to flow and all that. It's part of the modeling. Maybe in another class I will explain what is model based development, and also there is something called model based testing. So either a model or it's a paperwork or a issue or diagrams, whatever it is, to make it realize that this specification will have a exactly mentioned requirements, that is the needed SRS, the needed design as a prototype. So we will with these iterations, with the help of updated system specification, we will have a SRS. So don't get confused with the system specification. System specification could have something like a system level. I will try to just explain what is the system specification. System level information, such as it could be an electrical requirement, it could be an hardware requirement, it could be mechanical, it could be performance, it will also have software. So all this will be part of the system. Basically, in embedded software, will take care of the software. Also, for doing the software, some of the feasibility that we need to raise whether I can perform this software on the underneath system. Underneath the system will have electrical, hardware requirements and all that. So these are some of the system level information this will be having, but we need only the software related things. That is why we will have concentrating on software requirement specification, SRS, detailed design, and the source code, all specific to software. And for as far as the testing is concerned, we will use a test case test procedure and a prototype result of in terms of a test result. So this will be iterated. As I said, it's an iterative model sort of a thing in the prototyping life cycle. The evaluation is with the help of a group of test cases procedures that will be used for evaluating it. So this will go in cyclic way or iterative way. Once this is done, what we do is specification will review or we will do a evaluation. So if the specification is final, if it is not, then again we will iterate on that. Actually, iterations of defining specification items, how it can be realized. So we need to have a justification, feasibility, realization can be feasibility, etc. These are some of the important items that needs to be taken care for this iterative process. Okay, so once these iterative items are done, then once this specification final says yes, then we are good to have a finalization of the prototype. That means we have a defined set of or an initial working model of the SRS, a proven concept of design, and a source code. To an extent it is working fine, and we have few test cases, sample procedures and reports which could validate the system to say that we have a prototype finalized. So these are some of the prototyping life cycles example what I have depicted here that will be used before we go into the next life cycle, which is nothing but formal life cycle. So I repeat, we start with an entry into the prototyping life cycle with a system specification. I will put a different color, it should be easy, green. So that is system specification, which will enter into the prototyping software life cycle. So we will do an initiation. That means we will initiate with the prototyping life cycle. We'll come up with an initial SRS and detailed design. It could be architecture. Then on these initial SRS or design or source code, we start the iteration. We define it, each of the requirements of the specific functions or features that are required as part of the system. I said the system will have many high level system level information, out of which we will consider only the performance of software related items. That is the goal of this prototyping. So we do update of the SRS, DD, source code, test procedures, sample test procedures, and sample results. Then we'll evaluate against that. If that is fine, or if that requires any updates, we'll take this path. We'll come back again. We'll take this path. We'll come back. So like this, we'll continue. Once everything is final, we are good to go for finalization, and we'll have a final or proof of concept working prototype, which will result in final SRS design or architecture document, a basic code, and a sample test case with the results. So these are all some of the prototype items. Okay, so we are done with the prototype life cycle. So we know that the next one is the formal life cycle, which is an important aspect of the embedded software systems. You may wonder why we need a prototype life cycle. So what will happen is, if I have a system and I have a customer requirements and I don't have a confidence to start, and I cannot commit, say in 6 months I will develop a small embedded system and I will deliver. It is not easy actually, and there has to be a thorough analysis, uh, proof of mechanism, etc. For that, what we do is we will develop a small prototype. It is really a shortened version of the actual life cycle, and we will stall at certain stage, and we say we are good to start the formal life cycle. And prototyping to formal life cycle can happen any stage. You don't need to have everything in place. Sometimes what will happen is you need only architecture and SRS. You say that okay, this architecture is going to work. I don't need to implement it. But you have studied all the interfaces, signals, and everything, and you come to a conclusion that I am good to go for next life cycle. That is formal life cycle. So that is what the criteria. Criteria we need to define. All that criteria will be part of this prototyping life cycle. So with that, the prototyping life cycle ends for the embedded software systems before we start the formal life cycle. So what do we do in a formal life cycle? All formal guidelines and processes are established. That means what are the formalities that we need in terms of implementing the complete formal life cycle will be followed or established. Entry and exit criteria are defined. As I said, the entry and exit criteria, what are those? It is the conditions that must be there for each of the process item before it starts, and exit criteria is something like it should be complete before we start the next process item. So that will be defined in the formal process. We know that in prototyping we don't have an entry exit at all. So overall we have an entry, overall we have an exit. But in formal life cycle we have entry and exit for each of the stages within the formal life cycle, and the stakeholders are defined. Who is going to do what, and they will be identified as well. And that means what is the team and what are the skills that we should have. So those are all will be part of the stakeholder identification and definition. Basically, software lifecycle data is defined with data identification and data organization. So the lifecycle will have several or various type of data that is involved. So the data will be identified first, then how the data is going to be organized or managed for implementing the complete software lifecycle will be part of this formal lifecycle. So we will take up an example of formal lifecycle method, how it is. So we have a planning to enter. We know that what is planning. In one of the last session, I have told that there is a development or test plan, which will have all the environment, how tests will be used, what are the guidelines, checklists, process, everything will be part of the planning. Once we have the planning frozen, we will actually start with the formal life cycle. So I had put a simpler V life cycle. It is called a V life cycle. It how it comes. V is an interesting part. So basically, it looks like a V shape. It's a V shape. So why V shape is that as we go across the different stages in deep, it is going to narrow down. It is going to go deep with the final elements conjuncted. So that is why it is called a V life cycle. What are the items that are there in the V life cycle? So we have a specification. We know that software specification we are done in the prototyping. So we have a software specification. We have an analysis of the specification, which is nothing but the feasibility study and all that. As part of that activity, we have an outcome of SRS. And after the specification, we have design or architecture. This design also can be broken into high level or low level. Means high level design, low level design. It's also called high level design, low level detail design, or design, whatever it is. Once we have the low level design, we have the coding. That means coding is done after the low level design or design is in place. Coding is nothing but implementation of the intended design. So this is one side from the development perspective. So this is development perspective. We have a testing perspective. So this will go in conjunction for each of the phases. So how it goes is we have the SRS I told, and on par with that SRS or the high level requirement, we develop the test case and test procedures. So for doing the testing, we have the high level testing defined. At the high level testing, the input is SRS. We don't care about design, coding, and anything. We always look at this. So we will not consider any of the low level items. We all need to know the specification of the SRS to develop a test cases and procedures for high level. And an activity as such, the outcome is TR, test result. So this is at the higher level. Next, for design, we similarly develop an integration test case and test procedure. This integration also can have its own test case test procedure, and the outcome of that is TR. TR. So usually it is called ITP, integration test plan or test procedure, which will be part of this. For doing the integration testing, we will consider the design, high level design and low level design. Why integration testing is called? You know that there are different functionality wise or feature wise modules that needs to be segregated. Each module how they integrate or how they interact each other. Those details are all considered for developing the integration test plan. And as per the integration test plan, we have the integration test cases, test procedures, and we do the testing at this level. We don't care about higher level. Of course, the inputs from the higher level can be considered in terms of an understanding of the system, but to map with what we do at the integration level, we will definitely take design item as an input. For doing the unit testing, we have the source code or the implementation item. Sometimes what will happen is they also use the low level design for unit testing. So that depends on how you want to define. So what they do is they will further divide this block into high level design one block, low level design block. Low level design block they do it for unit testing along with the coding. These two can be taken care. But in general, source code is a prime input for doing the unit testing. Unit testing is also called as component testing. So each of the components or each of the units which are implemented or coded will be tested. So again they will have a test case, test procedure, and resulting in test result. And all this TR you can see on the right hand side will be on the right hand side and goes with the conjunction of these left hand side elements: specification, design, and coding. That's why it's called as a V model. So this is nothing but the formal life cycle. So we have prototyping done in the previous prototyping life cycle that will result in a formal specification. That specification is considered as an input. For that specification, we develop testing in parallel to all the items that are required in the development for doing the testing updates. So this is a formal life cycle example, and we know that why we need to have testing identified for each stage, because it's very important to identify the software issues or bugs at that stage, so that the cost of maintenance or the updates of the products will be less as we identify at the initial stages. So that is what is depicted in one of the earlier sessions. We have gone through this graph which has identifying the cost of software defect. It grows up as we go deep into the productization. We cannot afford to have a bug that is there in the product that is released, because the cost will be very high, because it has to go through several life cycle, or the bugs could be at any stage, a requirement could be wrong or something like that. So what we do is we will identify and fix the bugs at the stages as early as possible before we release the product. So that is what the story of this slide. The same thing is from the formal life cycle has been formal. Model life cycle, typically how it is there actually. So we have requirements, we have architecture or high level design, we have a low level design, we have an implementation. These on the one side. On the other side, we have for on par with the requirements, we have an acceptance test. On par with the architecture or high level design, we have system test. We have an integration test. We have an implementation and unit test. So a cut down version of this is being used here in the example formal life cycle. Here cut down is something like I had put as one block for design, which will be used for integration testing, and there is no system testing. So the same system testing is used here for architecture point of view. And requirements, I have used the acceptance, because acceptance report is required for the user or the customer. Here what I have to do is requirements is used for high level testing. So similar, but basically this is a model they use. This is from an example how it is depicted in a book called Introduction to Software Testing by Amman and Offord. On book is there. So this is the embedded V model life cycle, where we see again a V shape having left hand side development stages, on the right hand side testing stages. This will go in hand for each of the cycle. And what happens typically is that this will go in parallel. Why I say to do an acceptance test or high-level testing, we don't need to have the underneath version. So once this is done, for each stage we are going to start the acceptance test plan or the high-level test plan. The test plan can be developed for the particular requirements. So still the design and the implementation is under the way. We can still go ahead with the test plan. We can write it. So that will go in parallel to the requirements. Similarly, while the design is done and going for the implementation, the system test plan or the integration test plan for the low level design can be updated or it can be started in parallel to these items. Once we are done with the implementation, we do the unit testing and we will go with the actual testing to produce the results. So plans and procedures can be written in parallel with all these left hand side items. So that is about the V model. Here are some of the points which needs to be understood. The requirements analysis phase of software development captures the customer needs. As I said, all the customer inputs from the system perspective also will be used in developing the requirements and the requirements analysis. And acceptance testing is designed to determine whether the completed software in fact meets the needs of the requirements. In other words, acceptance testing probes whether the software does what the user wants. This is something like a business perspective. Acceptance testing must involve users or other individuals who have strong domain knowledge. As I said in one of the earlier sessions, the users or the testing team should have a strong system knowledge who can present the system to the customer or who can basically report the test outcome to the user or the customer. So it's very important that acceptance testing is used for delivering the product. Next one is the architectural design phase of the software, which uses components and connectors. That means the interaction of the various modules to realize the system, whose system specification is intended to meet the previously identified requirements. That means we have the high level requirements which will map with the different components as a interaction of the various components to come up with an overall design or the architecture design. On par with the architecture design, we have the system testing, which is designed to determine. Here, design means testing is designed to determine whether the assembled system meets the specification. It assumes that the pieces work individually and asks if the system works as a whole. This level of testing usually looks for design and specification problems. That means whether design has any flaws. All this will be identified in this testing. It is very expensive place to find lower level of faults and is usually not done by the programmer but by the separate testing team. That means system testing is done independently with an identified team who will not bother about the low level issues, or here low level issues could be any of the signals or drivers or hardware registers or the processor related things, but it looks at the system level as a black box. So there is a separate dedicated team who will take care of system testing, and that will be on par with the high level design or the architecture design. The next one is the low level design phase of the software development, which specifies the structure and behavior of subsystems. That means there are different sub modules which will have some structure and behaviors. All will be detailed in the low level design. So each of this will be intended to satisfy some functionality in the overall architecture. That means each subsystem or submodules will have its own defined feature or the function. And on par with each of these low-level design, there is a testing methodology called integration testing, which is designed to assess whether the interfaces between these modules in a given subsystem have consistent functions and communicate correctly. Let's take out this because it's additional information. So integration testing is on par with the low-level design, which will identify all the interfaces between these low-level modules on par with what is defined in the low-level design, and it is consistent, and the interfaces interface each other correctly and communicate appropriately. The last one is the implementation of the programmed elements in the phase of software development that actually produces the code. As a result of implementation, the exit is source code. On par with this implementation, we have unit testing that is designed to assess the units produced by the implementation phase and the lowest level of testing. In some cases, such as when building general purpose library modules or the low level source code, unit testing is done without the knowledge of the software applications. What it means is, as a low level unit, it is tested with the help of a parameter which will identify the flow within that module or the unit. So that is how the implementation, the unit testing of the implementation is done. I think I have explained in one of the sessions about unit testing, integration, and all that. Here is a mapping of all those types of testing in this model. So this will go hand in hand with this different life cycle process. So each life cycle will have an exit, which will be an entry for the next life cycle. That is what the entry and exit criteria that needs to be defined. So we will go through this entry exit criteria in the next session, of course. So what are those life cycle process elements that needs to be defined? So we know that each life cycle will have a process. All this in the V model. So what it is to have minimally, or what is a mandatory thing that is we need to have for the life cycle process for each stage. So there has to be an objective, there should be a scope, there is an entry criteria for that stage. So what are the inputs that are required? So what it is going to produce, what is the output? Then we have an exit criteria which defines the exit conditions for that stage. So we will take an example in the next session for each of the life cycle process, and we'll identify. I think I will explain about consumer electronics. I will explain about automotive, how the processes are there in the next session. So basically, these are some of the elements that are mandatorily used for embedded software lifecycle stages. Objective of the stage, scope, entry criteria, inputs, outputs, exit. So those are required.